Hello everyone, thank you for coming. My name is Federico Sejers. Within the controls community, multi-agent system coordination is an active area of research where one of the fundamental problems studied within this area is the synchronization or the consensus problem. With respect to the synchronization problem, it is the objective of a group of follower agents depicted by these triangles on the left to synchronize their trajectories with that of the leader denoted by the red square. It is then the leader's job to synchronize its trajectory with a user-defined trajectory denoted by this figure 8 in this example here. Here we illustrate a simulation of such a scenario. As you can see, all agents managed to successfully synchronize their trajectories. Among the assumptions made to enable this result is the implicit assumption that the coordination occurs in a neutral environment, which is an environment free of adversaries that are actively preventing or inhibiting the multi-agent system from meeting the objective. Next, we show the same scenario, except that we replicate the synchronization simulation in a contested environment. As you can see, all agents initially synchronize their trajectories. However, once one of the follower agents abandons the multi-agent system, the remaining agents are destabilized and they cannot synchronize their trajectories with that of the leader. While there are many ways to disrupt and inhibit a multi-agent system from satisfying or meeting their objective, within this work we focus on the Byzantine threat. In particular, we focus on two types of Byzantine agents. A type 1 Byzantine agent is an agent that executes the intended controller but communicates false state information about itself to its neighbors. Similarly, a type 2 Byzantine agent executes a controller that is different from the intended controller or executes the intended controller under the influence of faulty hardware, while communicating true or no state information about itself to its neighbors. So the overarching question we would like to answer is, how can we achieve multi-agent system objectives in contested environments with distributed controllers? Unfortunately, this question is large and consists of multiple complex layers, so within this work, we focus on a smaller, more manageable question, which is, how can we achieve formation control and leader tracking with Byzantine adversaries in the multi-agent system and distributed controllers? This now brings us to the problem formulation. Consider a heterogeneous multi-agent system composed of n follower agents and a single leader. The flow of information between the followers is modeled through the use of a time-varying graph G, which consists of a node set, an edge set, and a time-varying adjacency matrix. Note that the adjacency matrix consists of time-varying edge weights, which is where we will impart resilience to type 1 and type 2 Byzantine adversaries. The neighbor set of agent I is defined as the set of all agents J different from I, such that the distance between agents I and J is less than or equal to some communication radius denoted by Ri. The neighbor set of agent I can be partitioned through the use of two subsets, namely the cooperative neighbor set and the Byzantine neighbor set of agent I, which are denoted by Ci and Bi respectively. Note that the cooperative neighbor set of agent I is the set of all agents J in the neighbor set of I, such that the edge weight Aij at time t is non-zero. From the adjacency matrix, we can construct the graph Laplacian, which encodes the flow of information between the followers of the multi-agent system. We can then encode the flow of information from the leader to the followers through the use of a leader pinning matrix denoted by B of t. By summing the graph Laplacian and the pinning matrix, we can construct the connectivity matrix H of t, which encodes the flow of information between all agents in the multi-agent system. For example, if we have a multi-agent system composed of 7 follower agents and a single leader, the leader pinning matrix is a 7 by 7 diagonal matrix where the fourth diagonal element contains the edge weight between the leader and follower 4. The model of agent I is the control affine model with an additive disturbance term where Xi, Ui denote the state and control input of follower I respectively, Fi denotes the uncertain drift dynamics, Gi denotes the known control effectiveness matrix, and the disturbance acting on agent I is denoted by Di. The objective of this work is to design a controller for the followers that achieves formation control and leader tracking, is distributed and event triggered, and is resilient to both type 1 and type 2 Byzantine adversaries. Here's a list of assumptions we make within this work that are common and found within the literature, with the exception of the second to last assumption. It is an assumption that we introduced that basically boils down to agent I receiving R-1 redundant state samples from each neighbor that broadcasts its state. We can then design the edge weights to be a function of trust, which use multi-point authentication or the redundancy in state information to compute a degree of reliability for each agent. Specifically, given R state measurements for agent J, which is a neighbor of agent I, the disagreements between all R state samples of agent J is computed as depicted here. Note that the double sum enables the computation of the pairwise difference between all R state samples of the state of agent J at broadcast time TKJ. Hence, Psi ij measures the discrepancy in state information of agent J with respect to agent I. Here's an example of a two-point authentication scenario where the first sampled state is the communicated state and the second sampled state is the sent state. Hence, the discrepancy between these two states can be computed through the use of psi ij. We then define the set Sj, which collects all broadcast times of agent j that are between the current time and the current time minus at reset, which is a user-defined parameter. The trust that agent I has in its neighbor j is denoted by tau ij, where tau ij is set equal to 1 when Sj is empty, and tau ij is set equal to the normalized sum of decaying exponentials of the discrepancy when Sj is non-empty. Note that as the discrepancy stays close to 0, tau ij stays close to 1, and as the discrepancy increases, then the trust decays towards 0. While we could make the edge weights a function of trust, there are certain scenarios in which the trust model will not allow for the isolation of a Byzantine agent. For example, consider the scenario depicted here, where we have two cooperative agents depicted by blue quadcopters and one Byzantine agent depicted by a red quadcopter. Suppose agent J communicates false state information to neighbor K, and suppose agent J communicates true state information to agent I. Under the trust model, we would see something that looks like this, where agent J is not isolated from the cooperative multi-agent system, since agent I does not know about agent J's Byzantine status. However, we can then leverage common neighbor information in order to construct a reputation model which would allow for Byzantine agents to be isolated in scenarios as the one depicted above. The reputation model is defined as presented here, where the first term computes or accounts for what agent I thinks of agent J, where these computations are based on trust, and the second term accounts for what agent K thinks of agent J, weighted by what agent I thinks of agent K. And note that this comment is with respect to the example presented above. Note that the projection operator is used to ensure that the reputation that agent I has for agent J at time t is contained within a user-defined set. For example, if we select xmin to be 0 and xmax to be 1, we can then ensure that the reputation that agent I has for agent J, denoted by zeta ij, is contained within the interval 0, 1 for all time. We then define the edge weight policy as presented here. Note that the edge weight from agent J to agent I is set equal to the reputation value that agent I has for agent J, provided the reputation is above a user-defined threshold denoted by zeta min, and agent J is a neighbor of agent I. Otherwise, the edge weight is set equal to 0, which occurs when the reputation is below the user-defined threshold or agent J is not a neighbor of agent I. Note that the threshold, again denoted by zeta min, is selected within the interval 0, 1. Here is a reminder of the construction of the cooperative and Byzantine neighbor sets for agent I, which are functions of the edge weight policy, which depends on the reputation model presented earlier. There are several benefits to this construction, namely that exact model knowledge and knowledge of upper bounds on neighbor quantities are no longer required for detection as provided in our preliminary work, and moreover, the reputation model enables for the reintegration of rehabilitated agents. For example, suppose that agent J were to become a Byzantine neighbor of agent I. If agent J were to eventually start communicating true state information about itself to all its neighbors, the reputation that agent I has for neighbor J would then increase, and once it goes above the zeta min threshold, agent J would then be allowed into the cooperative neighbor set of agent I. We now arrive at the construction of the error signals, where the formation control and leader tracking error for agent I is denoted by E1I, and it is defined as the state of agent I minus the state of the leader minus a fixed relative position vector used to construct the formation. The estimation error for agent I is denoted by E2I, which is defined as the difference between the estimated state of agent I, which is denoted by xi hat, and the actual state of agent I. The controller of follower I is denoted by ui, where the first term within zi corresponds to a consensus-like term that uses a relative position offset to construct the desired formation. Note that this term uses local state information from the neighbors in order to coordinate. The second term within zi captures state information that is sent from the leader to follower I, provided follower I is connected to the leader. The zero-order hold observer that generates the state estimate of follower J is presented here, and the sequence of broadcast times for follower I is generated by the event trigger presented here. Note that phi2 and phi3 are positive parameters that can be found within the paper, and epsilon is a positive parameter used to exclude xeno behavior. Here we have the agent-level closed-loop error systems for the formation, control, and leader tracking error and the estimation errors for agent I. Note that both error systems contain consensus-like terms for the estimation error and the formation, control, and leader tracking errors. Note that the derivative of these error systems exist almost everywhere except at isolated times, which correspond to the broadcast times of the neighbors of agent I and agent I itself. The ensemble-level closed-loop error systems are presented here by E1 dot and E2 dot, where the stacked vector systems are presented here. We now arrive at the main result of the paper, which states that the trust model, reputation model, edge weight policy, state observer, and controller ensure that the multi-agent system formation, control, and leader tracking error is globally uniformly ultimately bounded in the sense provided here. Provided state feedback is available as dictated by the event trigger, all assumptions are satisfied, and the user-defined parameter conditions contained within the paper are satisfied. Here's a sketch of the proof where we begin with the Lyapunov functional presented in the first line, and after taking its time derivative and substituting in the closed loop dynamics for E1 and E2, we can obtain the upper bound presented on the second to last line, which in combination with the construction of the Lyapunov functional provides the UUB bound for the E1 error system. After performing a signal chasing argument, we can conclude that the control signal for each cooperative follower is bounded. We now present some simulation results where the objective within the simulation is to form the desired formation shown in subfigure A on the left. However, at the time intervals presented below on the bottom right, followers 3 and 5 will be converted into type 2 and type 1 Byzantine adversaries respectively, where it is then the goal of the remaining cooperative followers to form the corresponding component of the desired formation while tracking the leader. Here we present a simulation video that validates the result. Note that the purple square denotes the leader, the blue triangles denote the cooperative followers, and once followers 3 and 5 become Byzantine, their Byzantine status will be indicated by the color red. Observe that even though there are type 1 and type 2 Byzantine adversaries, the remaining cooperative followers construct the desired formation and track the leader. The figure on the right shows the trajectories of the corresponding followers for the simulation just shown here. Here we depict the trust, reputation, and edge weight plots for follower 4. Note that the corresponding plots for the remaining agents are omitted since they are similar to the ones depicted here. We first begin by looking at the trust plot on the top left, which shows that the trust that follower 4 has in neighbors 3 and 5 begin at value 1, and once Byzantine behavior is detected, they quickly decrease down to 0, where they remain so up until cooperative behavior is detected at the 40-second mark. Because followers 3 and 5 change to cooperative followers after the 40-second mark, they communicate true state information about themselves for the rest of the simulation, which causes the trust value to increase back up to 1. We then observe similar behavior on the plot corresponding to the edge weights, where once Byzantine behavior is detected, the values of the edge weights quickly decrease from 1 to 0, where they remain so up until after the Byzantine agents begin to demonstrate cooperative behavior, and once the reputation value clears a threshold value of 0.9, the agents are admitted back into the cooperative neighbor set of follower 4. Next, we show additional plots. The plot on the bottom left shows the norm of the formation, control, and leader tracking error for all agents. The large purple spike corresponds to the Byzantine follower 3, which is the agent that abandons the multi-agent system and remains stationary for a period of time. We can also see that the formation, control, and leader tracking errors for the remaining cooperative followers remain bounded in a UUB sense, where we can achieve formation, control, and leader tracking even in the presence of type 1 and type 2 Byzantine adversaries. The middle plot demonstrates the broadcast times for all 5 followers, where the plot on the bottom left, the bottom right corresponds to the broadcast times from time equals 0 to time equals 15 seconds, and we present this plot to better demonstrate the spacing between broadcast events to highlight the discrete communication nature of the followers. In conclusion, through the use of a reputation algorithm, we can achieve the formation control and leader tracking objective in the presence of both Type 1 and Type 2 Byzantine adversaries. Future works may consider the relaxation of the connectivity assumption, adaptive control techniques to improve performance, as well as other types of adversaries, such as those that can launch time delay switch attacks. This concludes the presentation. If you have any questions, please forward them to my email, which is fredzeg@ufl.edu. Thank you.